So today we're talking about specialized strategies for products of binary variables. For starters then, let's talk about the problem type of interest. So we're going to assume that all the variables are binary, but this is not a requirement in the sense that a lot of the ideas that we will go into actually apply if only a subset are binary. We then have an optional linear objective term, and then we have this quadratic objective term with no assumptions on the convexity or lack thereof. We then have optional linear constraints, and the problem can still be hard even in the absence of linear constraints. In fact, you can reformulate some standard problems that are MILPs with binary variables and linear constraints into unconstrained quadratic problems, also called QUBOs. And these actually are very good for certain types of solvers, such as the quantum annealer that is part of the D-Wave quantum computer, and the alpha QUBO solver, which is described in this link here. But for Gurobi, if you have linear constraints in the model, you're probably better off keeping them. Today, we'll start by going over some fundamental concepts that are useful for models of this type. Then we'll adapt a three-prong approach, which I think works for most difficult combinatorial optimization problems. And the first approach is to look at solver options and parameters to improve performance. If that doesn't work, we look at the existing formulation and try to tighten it or do something with it to make it solve faster. And if that doesn't work, we go to the more time-consuming approach that can also yield big dividends, which is to actually look at alternate formulations that solve faster. So what solution strategies do we have available to us here? Well, we can just solve the problem as the convex or non-convex MIQP that it is. We'll deal with the quadratic objective directly. If it's non-convex, that's not a problem for Gurobi, starting with version 9.0. We'll just solve it as a non-convex MIQP, and if the quadratic expression appears in the constraints, that too is not a problem. But we also have other options, namely to transform this problem into an easier convex MIQP or an MILP. The first such transformation option involves convexification of the objective. And there we make use of the fact that for a binary variable, the square of the variable and the variable itself take on the same value in any integer feasible solution. So what that means is we can add and subtract the square of a binary and the binary without changing an expression. So here we have a product of two binaries, and we add and subtract the square of both the first and second binary, and then we rearrange, and what we find is we now have a quadratic expression that is convex at the expense of subtracting off this linear expression of the binary variables. And what we just did for these two variables extends to arbitrary groups of products of binary variables. So in this case, we can add and subtract some positive multiple of the square of each individual binary variable and that binary variable itself. And then we rearrange to get a new quadratic matrix that has this diagonal matrix capital D added to it. And then we've subtracted off this linear expression involving the diagonals of this matrix capital D. And the net result is, again, we have convexified the objective. Now, first thought, you might think, well, this is great. We've moved from a much harder problem class, this non-convex MIQP, to a convex one, and we've done it without adding any constraints at all. But we did pay a price. So in particular, again, we have this linear term that we subtracted off, and this essentially solves a relaxed version of the model of interest that can be weaker than the one we want to solve. And to see this, let's just look at a very simple two-variable model where we've got binary variables. So if we look at this problem, just by inspection, we can see that the best possible objective value is in fact 0. And in fact, that is the optimal value with integer restrictions. We can set one variable to 1 and the other variable to 0. And we have an optimal solution to this very simple problem. But now let's think about what happens when we convexify here. If we convexify and relax, well, we can set the two variables to a half. And if we plug in a half into this convexified expression, we get an objective value in the relaxation of -1/4, less than the obvious dual bound that we know exists for this problem and that actually is optimal. So not only is this counterintuitive, but it indicates that what we've done with this convexification is created a weaker relaxation. And on the convexified problem, we actually would have to do some branching before we would be able to solve this problem to optimality, whereas that's not the case if we just dealt with the original problem. Another solution strategy we can use here, though, involves instead linearizing our problem from a convex or non-convex MIQP into a regular MILP. Let's start with the simplest linearization technique, which more or less corresponds to what Gurobi does when you set its pre-Q linearized parameter to 1. So you have a product of binary variables, and the product of two binary variables can only take 0 or 1 values. So it too is a binary variable. So we introduce a new binary variable Zij that we want to ensure always takes on the value of our original pair of binaries Xi and Xj. We can accomplish that by adding the following 3 constraints. And to see this, suppose we set one or more of Xi and Xj to 0. Well, then these first 2 constraints are going to ensure that this new variable Zij is set to 0. Meanwhile, the third constraint is always satisfied. The right-hand side is either going to be 0 or -1. So it's always satisfied and is hence redundant in that case. Conversely, if both Xi and Xj are 1, the first 2 constraints are always satisfied, but the third constraint is going to force Zij to be 1. So what this means is we can linearize by adding these 3 constraints to the model and then replacing each occurrence of Xi, Xj in the model with Zij. So we've gained because we can now benefit from these various Gurobi features that are available for this linearized MILP that are not in play for the MIQP, whether it be convex or non-convex. But we again have paid a price. We've added 1 to 3 constraints for each product of binaries. Now you might ask, well, wait, you've added 3 constraints. Why are you saying 1 to 3 constraints? Well, we can actually exploit the objective. So if the objective is pushing this Zij variable up or down, we can make use of that and not add all 3 constraints. So I'll illustrate with the third constraint here. So suppose we only add this third constraint and the objective is minimizing. It's pushing Zij down. Well, what's going to happen? Well, if Xi and Xj are both 1, it's just like before. Zij has no choice but to be 1 regardless of the objective. But suppose one or more of the Xi, Xj's is 0. Well, then this right-hand side again is 0 or -1. Well, the objective is going to push Zij down to its lower bound of 0 in this case. Remember, Zij is this new construct we've created. So if we only add this one constraint, that's the only place Zij appears in. There's no other constraint that's going to force Zij to stay up to be 1 in this case. So the objective rather than these two other constraints, can be used to push Zij down to 0. So that's why I'm saying 1 to 3 constraints, and Gurobi makes use of that. And then the argument is very similar if the objective is pushing Zij up, in which case we need the first two constraints, but not the third. So that's the simplest linearization. Let's now move to a less straightforward one that I only became aware of a couple years ago looking at this MILP model here. So this model basically involves penalty variables on soft constraints, illustrated by this one constraint here that is one of many in the model. So the objective function contains a continuous variable that is the penalty variable, in this case C25. All the other variables are binary variables that correspond to individual knapsack items, and then the coefficients here are the associated knapsack weights. We then have a knapsack capacity on the right-hand side, and it's important to note that there is also one really special item, in this case associated with this variable C697, where this variable has a knapsack weight that consumes all of the knapsack, whereas every other variable has a knapsack weight that consumes less than the total knapsack capacity, leaving some level of slack left over. That's a pretty complicated constraint to get a handle on, so let's look at a simpler version. So here we have a soft knapsack constraint with only 3 items. We again keep this notion of this special item that consumes all the capacity. And once again, we have our penalty variable for violations. And now the first thing we note is that if you only put 1 or 0 items into the knapsack, you're not paying any penalty. So the penalty is 0 there. So therefore, we can enumerate all the possibilities where the penalty variable takes on a positive value. 2 items are in the knapsack. There's 3 such cases, or all 3 items. And in each case, we can just calculate what the penalty will be, or the excess will be. And then we have to be a little bit careful about double counting. But what we see then is that this penalty variable actually can be expressed as this nonlinear expression of binary variables. So what we've done here is we actually have a multilinear expression in disguise by this seemingly benign soft knapsack constraint. So implicitly, we're minimizing this multilinear expression. Now, what does that mean when we go back to our original problem with all these things? Well, it gets a lot messier and enumeration is not so hard. And I still, quite frankly, haven't sorted out all the details, but all we need to know today is that now with this original constraint, we're actually minimizing this complicated expression involving linear combinations of all the bilinear terms minus linear combinations of various larger multilinear terms. So we're actually optimizing a very complex nonlinear MILP type expression involving the binary variables when we create these soft knapsack constraints. So there's a connection here. Now, I don't think the person who created this model was doing anything other than thinking about soft knapsack constraints. There's no information in the MILP set regarding where this model came from. But this raises a question. Can we modify this to help us linearize an expression involving just bilinear terms? And the answer turns out to be yes. So here's a modified version of the previous constraint. The only difference is we've changed the capacity, and when we change the capacity, we still ensure that this one special knapsack item that we had before consumes all the capacity. Everything else is left as it was before, and this new value is just the sum of all these knapsack weights that we see here, except for this special knapsack item. So what happens when we create this constraint? Well, now all those multilinear expressions that don't involve this special knapsack item, they do not fill up the knapsack constraint. You can pick any number of these other knapsack items as long as you don't pick C697, and you won't incur a penalty. You won't violate the knapsack constraint. And then on the other hand, if you do set this one special item to 1 and put it in the knapsack, then any other item you put in the knapsack contributes precisely its knapsack weight to the violation on the knapsack constraint. So what that says is our penalty variable is precisely this bilinear expression down at the bottom here. So in other words, the penalty variable represents precisely a quadratic expression involving C697 and the other binaries. So we can reverse this now, and basically for an arbitrary expression involving linear combinations of pairs of binaries that share a single binary variable y, we can create a linearization by introducing a new value q that is the sum of all the individual coefficients of this expression, using that value q as the knapsack capacity, assigning to this special binary y that appears in every bilinear term in this expression, assigning to this variable y the knapsack capacity, and then using the coefficients on the remaining binary variables. And what we've done is then our penalty variable is precisely this expression involving n bilinear expressions. So we've got a new way to linearize that basically handles multiple bilinear terms with a single constraint. So that's what we have with the Gurobi's pre-Q linearize 2 setting. And what we've done is we're able to model multiple bilinear terms with just one additional variable and constraint. So that's a big plus. It's more compact. We've got the gain of moving from a non-convex MIQP to an MILP. This contrasts favorably with Gurobi's pre-Q linearize 1 setting, where basically each bilinear term introduces a new variable and 1 or 2 additional linear constraints. So this is much more compact, but again, there is no free lunch in the sense that what we found is this formulation of the MLP tends to be weaker than the one where we generate additional constraints and variables for each bilinear term. So there are trade-offs here, but each has its own advantage depending on the nature of the model. And then again, we also have this setting associated with setting Gurobi's pre-Q linearized parameter to 0, where we do this convexification and we're moving from a non-convex problem to a convex one without adding any constraints. But there also are the downsides that we miss out on some MILP features that are lacking from a convex MIQP solver, such as Gomery cuts, for example. And then we also saw how you get these counterintuitive bound values associated with a weaker relaxation. And we can see which setting is in play, whether we chose it ourselves or we want to know what Gurobi decided. So the no log will tell us what Gurobi decided to do. So all you need to do is compare the original model, which shows up really at the start of the optimization log, and then look at the pre-solve model, since pre-solve performs the linearizations in question. So in this log, for example, we see that there are no new additional constraints. So that tells us that Gurobi chose to convexify. In our next log here, what we see is that there are, so this is for the same problem, by the way, and we see that in this case, there are new constraints and basically one new constraint for each of the quadratic objective terms involving products of binaries. And then lastly, here in this log, again, the same model, we see that there are new constraints and new variables, but not one for each of the over 1,000 quadratic objective terms, significantly less than that. So that says that Gurobi selected this more compact linearization involving the soft knapsack constraints. All right, so that ends the section on sort of the basics. I'm going to pause briefly to answer any questions that relate to this material right now. This is a good sort of break point. So if you have a question on the slide, post it now. If you have broader questions, I'm going to handle it at the end of the presentation. Okay, so looking at the questions, can Gurobi handle multiplication of continuous variable and a binary variable? And the answer to that is yes, it will handle that for you. How can we assume that Q plus D is PSD? And the answer to that is that there always is, you can always make D big enough to compensate for whatever indefiniteness there is in Q. So Gurobi starts by basically making D really large and then uses heuristics to find as small a D possible that ensures that D is positive semi-definite. Could the pre-Q linearize parameter reduce cubic or higher order terms since the products are binary too? And the answer to that is yes, it could, but it does not currently do so. But you are definitely on target, and there's some work in the literature that shows that you can, handle higher order terms as well through the linearization techniques that we described. But again, I want to emphasize that this soft knapsack constraint approach may be a more compact way to do that rather than sort of trying to linearize using some of the larger number of constraints. How well do these rules scale as the problem size increases? I will get to that in subsequent slides, so I'll defer that there. Does Gurobi run all methods automatically, or people have to set the parameters in advance? I don't think we try all of them. I think we look at the model, because the bottom line is even if we tried all of them, we can't tell just by looking at the resulting model size which is going to be best. Okay, the next question has already been answered. The next one is asking about quadratic assignment problems. I will touch on that later, so I'm going to defer that one. And then can you compare the dual bounds for that one problem with the 3 pre-Q linearized settings? And the answer is yes. You can just start the run and let it run and just take a look at the initial bounds. How do these compare to the McCormick relaxation? Actually, if you plug in the McCormick relaxation for products of binary variables, you get that basic linearization that we looked at. How does pre-Q linearize interfere with pre-MI QCP form? I'm going to have to defer that both for the sake of time, but also because I actually would have to look up the answer to that one. So, okay, I think it is time to move on. So here, now let's move on to an example problem that illustrates some of the things we've discussed. This is called the p-Dispersion-Sum problem. The goal is to basically take a set of endpoints with distances dij between the points and find a subset of k points that gives you the most diverse collection of points of that cardinality k. One metric we can use involves maximizing the sum of the distances. So the model formulation indicates that we'll associate a binary variable that is set to 1 if we select point J to be included in our subset. So there are n binary variables in this way, and we just need to add one constraint that the sum of these binaries is equal to k. And then our diversity metric gets increased if both points are in our selected subset of k variables. Then we'll add the associated distance into the metric we're trying to measure, and this is the problem we want to solve. And here are 2 links that discuss this further. I'm going to focus on the second one, which we will come back to subsequently in a few minutes. But first, what are our options here? Well, we can solve this directly as a non-convex MIQP. Just set Gurobi's non-convex parameter to 2 and let the spatial branch bound run. But on most of the models here, this really is not the best approach. Instead, we want to make use of some of these concepts we looked at to transform the problem into an MILP or a convex MIQP. So we can choose between the convexification and linearization options we saw previously and their strengths and weaknesses. And I want to go into a little bit more some of the strengths of the linearization approach. In particular, because it's an MILP, we have more opportunities to apply these polyhedral-based cuts. And Gurobi's RLT and BQP cuts are particularly effective when, in terms of raising intensity on these particular models, not only with products of binaries, but with general bilinear terms. And then if we use pre-Q linearize being set to 1, we are introducing a lot of constraints with plus or minus 1 coefficients, which is a case where aggressive 0 half cuts tends to be very effective. So these are some important parameters to sort of keep in mind in our toolbox when solving these types of problems. So how do we do on this problem? Well, I took the example from the blog page that I mentioned in that previous link, which has 50 points and a subset of size 10. And Gurobi's default choice was not that good. It actually ran out of memory with a large gap after over an hour. And it was pretty clear that if we let it run much longer by spilling nodes to disk so that we didn't run out of memory or ran on a bigger machine, that it wasn't going to finish anytime soon. Gurobi chose to convexify rather than linearize. Both linearization options were better, and the best I found was to use the compact linearization and also add aggressive RLT cuts, one of the particular cut types that we mentioned as being valuable or useful for these types of problems. But given the small size of this model, this is a pretty unspectacular result that begs the question of whether we can do better by tightening the formulation. Well, how can we tighten the formulation? We have this formulation on the left, and it poses a particular challenge, which is that the vertex points of the relaxation here are already all integer. So any notion of LP-based polyhedral cuts on this direct formulation aren't going to work because they're based on finding facet-defining inequalities that actually cut solutions off from the relaxation, and there's nothing to cut off. It's already a convex Hall of integer points formulation. And we already saw that if we just linearize, well, that's not enough. So if you go to this link, which is a blog from Erwin Kalvelagen, which is a very good blog for many other posts besides this one, it describes multiple ways to actually look at the linearized formulation that has these new variables Zij. And if we're willing to work with those variables, we actually can generate a cut that enables the solve time to go from hours to less than a minute. And the blog describes multiple ways to derive this cut, but we want to do it in a manner that's generic, that maybe we can understand to the point where we can extend it to use on other models that are different from this one. So I'm going to look at two different ways to generate the cut. The first comes from the blog itself, and basically it uses an approach that is in line with reformulation and linearization, this notion of RLT, where we use that idea and we aggregate constraints. So our original formulation is on the left, our linearized formulation is on the right, and we want to find out, well, how can we derive this cut? So what we do is we start with our cardinality constraint, and then we create n new constraints, where in each case we multiply this constraint by one of the binary variables. So we do that for each of the n binary variables, and then we just make use of various facts that are present in this formulation. The first being that the square of the variable, the multiplier variable xi, is just equal to the binary itself. So we can pull xi out of this summation, and then we have an xi squared term that we replace with xi and then move to the right-hand side. So our right-hand side now becomes k minus 1 times xi. And now we have all these products xi, xj here. Well, we can replace those with the linearization variables that are equal to those products, namely the zij's. So we've gone from this sum of xj's times xi to a sum of these zij variables. And then we add up all n of these constraints. So we get this summation. Well, now that we've got this summation of xi's here, we know that that equals k. So we can replace this term here with k here. So now we have this collection of these sums of zij variables being k minus 1 times k. But if we look at this and note that zij and zij and zji are the same thing, because the product of xi and xj is the same as the product of xj and xi, we can replace this sum with 2 times the sum of the j's that are greater than I of zij, and then we just do a little bit of rearrangement, and out pops the cut that we use to get better performance. So that was a bit sort of complex, a bit messy, but it is generic and effective. We could try it on other models and potentially have success. I now want to talk about a second approach that does not appear in the blog, which is to use the so-called Padberg graph that is described in Padberg's Boolean quadric polytope paper. So here we have our original variables xi and xj, and we associate nodes in the graph with each binary variable in the problem. And then for every pair of binaries that appear in a bilinear term, we connect the two nodes associated with those binaries via an edge that we associate with the new linearization variable zij. And we'll see how this works in the next slide. What I want to emphasize is whichever approach we use here, we're ultimately doing the same thing, which is determining the number of new linearization variables z that must be 1. So for our dispersion problem, which again appears here in the upper right, our Padberg graph is a complete graph since every distance between 2 points is positive. So basically, every pair of variables has a bilinear term in this objective up here. So now we ask the question, given that we have this constraint that k of the x variables must be 1, how many of the z variables must be 1? Well, it really doesn't matter which kz variables we pick. The answer to that question is going to be the same. So without loss of generality, let's pick the first k x variables, set those to 1 and see what happens. And what happens is I've highlighted the X variables that we set to 1 as nodes in green, and this induces a complete subgraph in its own right. So the green nodes are a complete subgraph, and therefore all we need to do, given that each edge is associated with one of these Z variables, is we just need to count up the edges in this subgraph. And that's a straightforward algebraic exercise, and the answer is precisely k times k minus 1 over 2, the right-hand side in this cut. Now, Padberg himself in this paper actually used this graph differently, and he used it to generate cuts when the problem has no constraints whatsoever. So he just looked at the quadratic expression, and for example, he looked for cliques like we see here. So here we have a 3 clique, and what he showed is that when you have a clique of size 3, the sum of the X variables minus the sum of the Z variables in the clique is less than or equal to 1. And you can extend this to larger cliques. You can prove it either by contradiction or induction or using some of the zero half-cut machinery, or as Padberg did, via facet defining inequalities. Now, Gurobi's BQP cut feature makes use of this for clique size of 3. And the nice thing about this is it gives you traction for cut generation, even when a model has few or no constraints whatsoever. Now, we recently found that actually cliques of size 4 or more may be useful. And with Gurobi 911 and later, we introduced a hidden parameter or an undocumented parameter you can use to generate more of these cliques. And we found that to be effective on certain models. Now, this will be more integrated in the next major release, so you will no longer need this hidden parameter. But for now, if you have Gurobi 911 and you have some models that you think fit this bill, give this a try. And if you're willing to share some models with us, this is sort of an ongoing development effort. We'd certainly be interested in hearing from you, or letting you maybe be an early tester of the next major release. Okay, so how well did this approach work? So our target time was just over an hour and a half. That was the best we did with parameters. And basically, there were 3 different approaches I tried, and all of them solved it in under 20 seconds. And what I found was the best approach was actually to add all 3 of the linearization constraints as well as the cardinality cut. And that dropped the time down to 5 seconds. So we were starting with this problem that took hours, and we're now down to 5 seconds. Now, the success we had there begs a couple questions. First, does it carry over to other models? To answer this question, I took a look at the QP-Lib model test set on the Middleman benchmark and focused on the models where Gurobi struggled, exceeding or coming close to the 1-hour time limit that was used on that benchmark. The first model I looked at, parameter tuning, cut the time in half. And again, 2 of the cuts that we described before as being specifically useful here were the key to getting that reduction. However, in terms of tightening the formulation, I was not successful, I think primarily because in this model, all the original binaries can be set to 0. And if all the original binaries can be set to 0, all the bilinear terms can be set to 0, which means all the linearization variables can be set to 0. So any notion of a cardinality cut on the minimal number of linearization variables being a positive value was not available in this case. Now, moving on to the next model, again, the parameters that we discussed did enable a performance improvement, but in this case, it was only about 20% relative to Gurobi's default choice. And in terms of tightening the formulation, this model lacked the explicit cardinality constraints that were present on the original variables in our dispersion model. So that wasn't directly available there. Furthermore, the Q matrix was not dense. We exploited the density in the dispersion model to make use of the Padberg graph. So the Padberg graph, while it actually could be used to figure some things out, it was much more difficult to use it. And in fact, there really is an easier way in this case, which is to ask the basic question that we asked there, which is, what is the minimum number of linearization binaries that must be set to 1 in a feasible solution for the linearized MIQP? And we can answer that question just by formulating and solving a submip to give us the answer. So here's our original formulation on the left. And then here's our linearized formulation. So what's happened? We still have the original variables. We've now added these linearization constraints and introduced these new variables z. So I'm just leaving them in generic form. And then our original quadratic objective is replaced by this linear objective involving the z variables. And now to go from this linearized formulation to answer the question, how many z variables must be set to 1, just involves replacing the objective here with minimizing the sum of the z variables. So this is the submip we solve. We get an optimal objective z star out of that submip. And then we add the cut that the sum of the z variables is greater than or equal to that optimal submip objective value. So our target time was 22 minutes and 40 seconds. And adding the cardinality cut with various different approaches yielded significant improvements. The best result being, again, adding the cardinality cut to the 3 constraint linearization model dropped the time down to just under 9 minutes. But if instead we just use the model with the more compact linearization that only used 1 constraint, we still dropped the time to under 16 minutes. So we got a gain there. And both of these times include the submip solve time, which of course has to be included in our measurements and was quite reasonable for these models, checking in at 32 seconds. I then moved on to a couple other models that were challenging for Gurobi, and let me just skip to the final summary table. And the results were good there. Again, the cardinality cut gave us speed ups on the order of basically 3 to 5 for these 2 models. So basically of the 4 models we had, all 4 of them, we could get performance improvements by adjusting the parameters that we discussed earlier as being specifically effective on these types of models. But then on 3 of the 4 models, this cardinality cut based on the submip was the best way to go. Now, I've started to look at some other problems, and in particular, quadratic assignment problems are interesting because they are known to be really hard for MIP solvers. And the good news here was I found that the submip solved quickly, and this enabled me to get some big speed ups on some problems that Gurobi could previously solve. And it also enabled Gurobi to solve problems that otherwise it could not solve either with defaults or with at least the best parameters that I found so far. It's not really a breakthrough because it doesn't scale up to larger quadratic assignment problems. The submip cuts require this basic linearization, and as you increase the dimension of the quadratic assignment problems, basically the growth in the linearized model grows quadratically as the dimension increases, especially if the quadratic part is fairly dense, and it becomes a node throughput issue. So I think this has promise, but only if we figure out a way to solve the node relaxations faster. So here I'm trying to answer a question that was posed in the earlier question break. And then secondly, on the negative side, we had some proprietary models from a prospect that I won't describe, but in this case, this approach was not effective because the submip solves were just too hard. They were really hard MIP models in their own right, so we couldn't get a cut in a reasonable amount of time. On the positive side, the extended BQP cuts that I mentioned earlier were very effective. Let me pause again for questions here. That sort of ends the section on working with the existing formulation. So I want to take a pause for any questions at this point. Okay, I may have missed this, but doesn't pre-Q linearize 2 still need pre-Q linearize 1 when evaluating the resulting bilinear terms? No, it does not. If you work through it, these are completely separate approaches. I can't really go back into the details here. My recommendation is the slides will be available, and go back and look at the little soft knapsack constraint with only 3 items and work through that. And I think you can convince yourself that these approaches are completely separate. Okay, the next one is sort of hypothetical. I'm going to hold off and wait on that one and answer it at the end. The next one, can the Padberg approach be improved when the objective is convex? I haven't really thought of that, so I don't know. I will defer that one probably and try to think about that and respond by email. How can you automate the cardinality cut generation within a workflow? Does this currently require running the same problem twice with different objectives? Well, I think we talked about basically 2 approaches, either the RLT approach or the Padberg graph approach to generate the cardinality cuts. When I worked on this, I used the Padberg graph approach, and I used Gurobi's Python API and also the NetworkX graph package and constructed the Padberg graph and had NetworkX enumerate the cliques for me to generate the cuts. Can you please clarify whether or not selecting non-convex equals 2 disables reformulations via pre-Q linearize? I believe the answer to that is yes. I think that's all I have time to say about that right now. Do these apply if one or more of the variables are non-binary but integer? Yeah, that does make it more complicated, but you can always express integers as linear combinations of binaries, and then you can linearize. So I think Gurobi does that. And okay, I still see a ton of questions, and we're coming close to the hour. So I'm going to have to stop here and finish my presentation and then see where we're at as far as answering additional questions. So the last section is on reformulation. So let's return to our p-Dispersion-Sum problem. And, we had this cardinality cut that was successful on the 50-point subset of size 10 instance, but does it scale well? And I found that the answer was no. When I bumped up the number of points to 100 and the subset size to 20, we did get a better gap, but this model instance did not solve to optimality in several hours. But if we're willing to step back for a second and say, well, do I really need maximizing the sum of distances as my diversity measure, or can I replace it with something else? Then we can make some progress on that. And again, I'm referencing Erwin's blog here, and he describes this nice reformulation where instead we'll maximize the minimum distance among the k chosen points. So we introduce a new variable delta that's going to be the minimum distance. So we want to maximize it. And then we need to ensure that delta is less than the minimum distance among the k chosen points. So we need a constraint that is only binding when the binaries associated with a pair of points, xi and xj, are both 1. And this constraint here will do it, because this constraint is only binding when we set both of these to 1. Then this big M term goes away. Otherwise, this big M term makes this constraint redundant. And before you raise the red flag that, huge big M values are a problem, we can just set M to be the maximum of the dij's in our input data. So this will do the trick. We just keep our cardinality constraint in our binary variable declarations as we did before. And there's even more good news here. We actually can do better. So we still now got a quadratic constraint. Now, it did turn out that this formulation actually worked really well and got the time under a minute, but we actually can get rid of this quadratic part and replace it. So we need this condition that the constraint is only binding when xi and xj are 1. And this constraint will do the job. And now we have a linear expression, and 2 occurrences of big M are still not a problem, because big M can be chosen in a small way. And the second formulation actually drops the time all the way down to 2 seconds. Okay, just wrapping up a couple loose ends. We saw how direct access to the linearization variables can help performance sometimes. And while you can work on the pre-solved model, you may want to just do it yourself. And here's 40 lines of Python code that show up in bigger print in the appendix, so it's not hard to do. And that being said, we're still investigating, trying to understand why this larger linearization helps. And we're hoping to sort of be able to figure out how to get the tightness that that gives without actually the additional constraints. So there's an ongoing effort there. And then lastly, I also want to mention that there are this notion we saw with the soft knapsack constraints of MILPs that are actually MINLPs in disguise exists elsewhere. There are other cases, including models with overlap or interference conditions, logical conditions like in SAT models. I mean, after all, Zij here is basically an AND condition on Xi and Xj. And then here's another model that is an open MILP model that fits this bill. And I'm not saying that if you have an MILP like this, you actually want to create the MINLP and solve it, but rather you want to use information from both to improve performance. Okay, so wrapping it up, what we saw is there are a lot of specialized strategies for models with products of binaries. We saw a bunch of specific non-default parameter settings, saw how there are various opportunities to tighten the formulation. You have linearization, you have convexification, and you have trade-offs between each. We saw 3 different ways to tighten a formulation: the RLT type approach, the Padberg graph approach, and the submip approach. And then on the reformulation side, the key takeaway is make sure quadratic conditions involving binaries are really quadratic. Erwin's blog gave us a good example where we actually could get rid of the quadratic thing, but yet really use a very similar metric. And again, this notion of MINLP formulations in disguise, giving us information about the actual MILP formulation being used. Here are a few references that might be useful. So if you want to take a deeper dive, do that. So thanks for listening, and I hope you found that useful.